Chapter 2, which was about free vibration, and we discussed the undamped and damped free vibration, and the last one we did was about Coulomb damping. In the free vibration, we looked at the amplitude and the frequency of excitation, or sorry, the frequency of oscillations. And the frequency of oscillation is either omega n for undamped, or omega n again for Coulomb damping. So even it is the last one, but the frequency of oscillation was omega n, or it is omega d when we have underdamped, and omega d is 0 for overdamped and critically damped. So that's what we did. And regarding the amplitude, we find the peak, the maximum, and we call it the amplitude. For underdamped, the amplitude is the beginning of the cycle, is the amplitude of each cycle. So it varies. For undamped, the amplitude is the same. And the frequency, if I just focus on the frequency in the free vibration, it was a function of the system parameters. For the spring mass system, it is function of K and M. And we assume it is constant for linear system and independent on initial conditions. So this was the initial frequency. Now in force vibration, there are different types of forcing. And as I told you in chapter 1, a force, the system is called under forced vibration if there is excitation. A dead weight is not a force that will cause excitation. So the characteristics of a force here, it means it has an amplitude, let's say in a Newton, this certain value in Newton, and also it is applied with a frequency. And an example I think I gave you in chapter 1 about the imbalance. Okay, imbalance, we will talk about it here. So that is the characteristic. It has an amplitude in a Newton, or it has a frequency of excitation. Harmonically is one harmonic excitation is one type, but there are different types. So we will focus on harmonic excitation. That will be the beginning to study the force vibration. Then you can move on to more types. So harmonically, as you know, is when the force is equal to F naught sine omega t. So harmonic force excitation. Can intervene the time. Okay, just hold on. I have to fix the Okay, so harmonic excitation. The type of the force is called harmonic force excitation. Okay, it is going to be given as F equal to F naught sine omega t. Okay, sine omega t. Or F equal to F naught sine omega t. Both functions here are harmonic. Sine or cosine are both harmonic. But we will take, the simple form, either sine or cosine, not the combination. Combination becomes complex, harmonic. So as you can see, this is the type of the force. We have the amplitude is here. And this is the excitation frequency. Okay, and it is given also in radian per second here. Okay, so the source of the excitation now, or the source of vibration, comes from this force, not the free vibration. Okay, the free vibration will be will start if you have initial conditions. Here, even if the initial conditions are 0, and the force is applied, then the vibration will be due to the force. Okay, so this chapter deals with the response of a single degree of freedom. We will limit this to single degree of freedom up to chapter 4. System subjected to harmonic excitation. When a system is subjected to a harmonic excitation, it is forced to vibrate at the same frequency as that of the excitation force. We call it omega. Okay, so the system has internal frequency. We call it omega n. That's characteristics of the system, internal frequency, which is function of K and M, or function of L and J for the rotating, for the rotational vibration or torsional vibration. Okay, so there is omega here and there is omega n. Omega n is the natural frequency. And omega is the excitation frequency. Okay, so the system under harmonic excitation, under harmonic force, is going to oscillate with omega, not with omega n, unless omega equal to omega. Okay, so it can be greater than omega. Omega can be greater than omega n, can be less than omega n, can be equal to omega n. Those are the three cases. The common sources of harmonic excitations are the unbalanced and rotating machines. And I think we talked about this. And forces are produced by reciprocating machines as well. And motion of the machine itself, which causes vibration to the base. And it will cause, it becomes a source of vibration to other machines. Okay, so those are listing of some of the sources of excitation. Now, so we have here either that omega is less than omega n, or omega equal to omega n, or omega is greater than omega n. Only those are the three cases. Those are not three numbers. Those are range. Yani omega less than omega n is a range, and omega equal to omega n is a specific value, and omega greater than omega n is a range. So the amplitude, it depends on where is where omega lies in which range. The amplitude will be different. Okay, the amplitude here, omega is less than omega n. The frequency omega, the response of the system will be faster than the frequency, because if you let the system to oscillate under a free vibration, it will complete cycles per second faster than if it is under omega. So it will be slower. The system will move slowly below the period of oscillation of the system. And if omega equal to omega n, this is exactly the same. And omega greater than omega n, we will have the system will move faster than its internal natural frequency. So we call this in phase, that the system is for omega less than omega n. This you can imagine this is a spring mass system, as an example, and there is a force equal to F naught sine omega t, accordingly, there will be x. According to the applied force, there will be x. X is a function of time. So it will oscillate. Okay. The amplitude here depends on, okay, the amplitude here depends on the range of omega. Is it omega less than omega n or equal to omega n or greater than omega n? For omega less than omega n, amplitude will be as compared with, with this range or this omega equal to omega n, which is called resonance, it will be less. And omega greater than omega n is called out of phase. Okay, so let me just explain in phase, out of phase, resonance. In phase, when omega is less than omega n, the force, as you can see, is a sine wave. So if you plot omega, if you plot f, it is a sine wave with a peak equal to F naught. That is the amplitude, and the frequency is omega. In phase, it means also the x will be sinusoidal as well. Sine, and we'll have if f is positive, then x is positive as well. If f is negative, then if f is negative, x is also negative. That means since the frequency is less than omega n, the system is in phase. It is not lagging, especially if there is no damping. It will not be lagging the force. It will follow the force. So if you are pushing slowly, less than the nature frequency, the mass will move with the force. If the force is upward, the mass will move upward. If the force is downward, the mass will move with the force downward. So this is in phase. Out of phase, okay, out of phase, it will be in opposite direction. Okay, this is out of phase. If the force is in the positive direction, the mass is, the mass is slower than the force. The response of the mass is less than or slower than the force, the excitation frequency. So the system will lag. Alaykum salam. The mass will lag the force. So if the force is positive, the system is still in the negative direction. And if the force is negative, the mass is still in the positive direction, so it is lagging. And there is the case when omega equal to omega n. That's called resonance. The amplitude here is the greatest. Okay, this is the greatest amplitude will be in this range, in omega equal to omega n. So if you call this amplitude A1, and you call this A2, and you call this A3, A2 is greater than A1, A2 is also greater than A3. This A2 is the greatest amplitude can occur. You are not changing F naught here. Suppose F naught is the same, that is the amplitude of the force. The effect of omega on the amplitude will be greatest when omega equal to omega n. That is called resonance, and that is the most dangerous case. Okay, so resonance is the case when excitation frequency, which is omega, equals to the natural frequency omega n. That's called resonance. That means reaching the maximum. That is the meaning of resonance. And so what we have at resonance, we have large amplitude develops, which is undesired. In most cases, that amplitude is undesired, or high or large amplitude is undesired. The reason why it is undesired because it will lead to fatigue, cyclic loading, and the spring will be under compression tension, and with large amplitude, it will break at resonance. It is to be avoided, resonance to be avoided in most cases, because it will lead to failure. If there is no escape, that means the system is to be operating at resonance, then you should have absorbers like dampers, viscous dampers, as we did in chapter 2. In free vibration, it is absorbing energy in the system and reducing the amplitude with time. So here it is the same. It will absorb energy and reduces the amplitude A2, the amplitude, as I called it here, A2. It will not decrease with time, but the overall amplitude will be smaller than if there is no damper. The other solution to this, to control the vibration amplitude is at resonance, is to use absorbers. Absorbers is adding another system. So the solution for resonance is to have spring damper calculated correctly. Okay, this to be calculated so that you reduce the amplitude of vibration. This is one way. And the other way is to have, this is called damper. And here we will have, this is K and M. We will add another spring and another mass. We call it K2, M2. And there is force here, F of T is applied. This is called absorber. So all the vibration, this is moving with X. Okay, this X is made equal to 0. Here you are reducing the amplitude X. Okay, reducing to minimum. Here you are reducing the amplitude to 0 almost with the vibration absorber. No, it is not in series, not in parallel. Because once you have two springs separated by a mass, this becomes, you are increasing the degrees of freedom. Okay, this is single degree of freedom here. This is called 2 degrees of freedom system. Okay, so let's say this is 1, and this is 2 degrees of freedom system. But this is a solution to control vibration, is to add another spring and another mass that absorb the energy from the first system, the original system. And this is called auxiliary. Okay, auxiliary, which is an extra. Not important, not as important as the first system. Okay, that is auxiliary. So this is the solution at resonance, to add a damper or to add a viscous damper. So damper is added, of course, during installation, not afterwards. So beforehand, this comes from design and then from specification due to manufacturing and installation. But the absorber can be added anytime, the vibration absorber. Okay, so let's see the equation of motion and how to solve the equation of motion if we have force vibration, harmonic excitation with force. Okay, the system will be spring mass system. This is the model with the spring K and damper C and M, and this is F, which is the source of the excitation. And the free body diagram, this is arranged vertically, so there is no, we don't need to put the weight because this is the additional force, Kx. There is Kx plus delta. And delta is not added here because mg is removed. They cancel each other. Okay, so k delta minus mg equal to 0. This is the equilibrium is used. So the new free body diagram will only contain the additional forces, which is kx, tx dot, the spring force, the damper force, and the applied force, if not sine omega t, and then you can apply Newton's second law, which is sum of forces equal to mx double dot, and we take the positive direction downward, we'll have minus kx minus cx dot equal to mx, I have to add f with it, plus f sine omega t. Okay, and then we rearrange, we move those two terms to the other side. And we get the differential equation, which is mx double dot plus cx dot plus kx equal to f naught sine omega t, where f naught is the maximum applied force. You take math 205 online? Online? Okay. So I'm sure you came up with differential equation, and this is not the first time we are doing differential equation. Chapter 2, yeah, computer applications, and in chapter 2 as well. But in chapter 2, this was 0. Let's call the free vibration. Homogeneous, yeah. So this is second order ordinary differential equation, but non-homogeneous. In free vibration, it is homogeneous. And of course, initial conditions are required as well. You know, x at 0 and x dot at 0 should be given. That make a complete system to solve differential equations. When you have a differential equation non-homogeneous, there are two solutions. The homogeneous solution, which is what we did in chapter 2, plus a particular solution. Okay, the homogeneous solution is by putting the right-hand side equal to 0. It is called complementary also, complementary or homogeneous solution, and which is exactly what we did in chapter 2. So we are not going to solve this again because we did this in chapter 2, and there are 4 cases. It all depends on zeta. If zeta equal to 0, there is x. Okay, so let me just call this. Total solution will be, this is xh, and this is xp, the particular, and the total solution is x, yeah, the summation, xh plus xp. Now we'll talk about xp later on, but xh is what we did in chapter 2, which depend on zeta. There are 4 cases for zeta. Zeta equal to 0, and that. Zeta less than 1, zeta equal to 1, and zeta greater than 1. And for each case, there is a different response. And for 4 equations. Okay, if I go to, let me go to the formula sheet just for a second here. Let me just make screen sharing. Okay, so this is the formula sheet, and there are 3 equations. There are 4. Where is, okay, this is the first one. Okay, so this is the one for zeta equal to 0. Okay, but this is not the one we should use for chapter 3, because the homogeneous solution, it means there are a constant. We should keep the constant that x equal to a sine omega t plus b cosine omega n t. This is the homogeneous solution without finding a and b, because a and b is found from the total solution, not from the homogeneous solution alone. So we don't use this solution where there is x0 here, x dot 0 over omega n. This is a, and this is b for free vibration. But for forced vibration, we should keep a and b as they are. We will find them from the total solution. Okay, and for for the underdamped, this is number 2. Okay, without using, this is, we just keep it as A and keep this as B. You don't find A and B. Okay, and this is for overdamped, which is, there is no changes here. This is for number 3. And and this one, this is number 4. Okay, you keep C and D. You don't use this one for the force vibration. Okay, we used with the constant. Okay, I don't want to save this. This is auto save. Okay, I will come back to this. Okay, so there are 4 cases for homogeneous. We don't find the constant here. Okay, it's still unknown. Okay, the constants are found from the total solution. Okay, let's come to the particular solution. The particular solution is given another name that is called the steady state oscillation. The particular solution is the solution that satisfies both sides of the equations, and it should be unique. You cannot assume something that is arbitrary. It should be unique because it depends on the right-hand side of the equation. So if the right-hand side is 0, then particular is automatically 0. There is no particular solution because the right-hand side. Yeah. Yeah, that is the trivial solution. But what is x? X depends on the right-hand side. The right-hand side of the equation we have here is sine omega t. X, the particular solution, is not derived like what we did in the homogeneous. We will assume it is exponential, and then we substitute, we find the value of s, and it might be exponential, it might be sinusoidal, it might be something else. The particular solution is xp is only sine omega t. There is no other solution, because when you put xp, it's an assumption. So let xp equal to t. Is this a solution? This is not a solution, because when you substitute in a differential equation, you will see that the right-hand side is not equal to the left-hand side. Then this is not a solution. Can we use exponential e to power t? Again, no, because when you substitute, there is no exponential term on the right-hand side, then it will be 0. Okay, so what you do is you assume that this is a constant multiplied by C. And then when you substitute in the differential equation, it will be m times 0 because second derivative is 0 for t. Plus, okay, let me just call it a. Then it will be a times c plus k times a times t equal to f naught sine omega t. Okay, so the right hand side is only sine omega t. There is no constant, then this is equal to 0. And there is no t, then this is equal to 0. This is the only way to make the two sides satisfied or equal. So the only assumptions we can do for the particular solution is to have sine omega t. So it is not by derivation, it is by matching. The right hand side contains sine omega t, then x equal to a sine omega t minus phi. So it will be of the same form, of the same function. This is sine omega t, then I'm using sine omega t, and that might be, it might have phase, and this is the amplitude in meter, and the phase in radian. Okay, so this is the assumption. The meaning of the phase, okay, if you assume that x equal to a sine omega t only, you are assuming that the phase is 0.
There is no cosine term.
Yeah, there is no cosine term. Okay, but this should be a proof that phi equal to 0. So you can just keep it as it is, phi, and unknown, and then it might be not 0 because one of the cases is not 0. So you keep it with the phi, with the phase. So that is the particular solution. The particular solution, we should look at the right-hand side. So this is assume the solution to be that is xp, not the total. Xp equal to x sine omega t minus phi. X here is the amplitude, the capital X, and phi is the phase. So it's just a matter of name. This is x is amplitude in meter. Okay, so we will talk about the solution. There are 2 minutes. I will keep this for next lecture. Okay, how to find x and phi.
ناقصين في اللي هو الحالات عن الفيز والريزونانس والعدد الفيز.
اوكي.
مثلا في اي حاله بنفكر انه ليش الديسبيسمنت مو الحين هو الفورسنج ايكويشن فاليوز اوف تايم لا؟ الفورسنج ايكويشن.
يس.
ليش الديسبيسمنت يتم امبليتيود مع نفس الشيء؟ ليش ما يتغير؟
It will change with time. It will change with time.
حتى لو اندعت.
حتى لو اندعت. حتى لو اندعت. Okay, it will change with time, but it will be periodic. You will see it is repeating itself. So you take the peak, that is the amplitude, the maximum. Okay, so when we talk about amplitude, we will talk about A or X. You know, I called it A here. He called it X. Okay, we will call it X. That is the amplitude. And as you know from homogeneous, the total solution is X homogeneous plus X particular. If you have, suppose, you know, just forget about this case. If you take those 3 cases, what is XH after some time? Is going to be 0. The only solution that will be existing is the particular. And the particular has X sine omega t, which is X is the amplitude. So that is the measure of the amplitude is here. And of course, in a practice or practical application, there is no z equal to 0. There is always damping. So this homogeneous solution will diminish with time. After some time, it will not exist. Okay, and the only solution that will stay is the particular, which is sine omega t with phase. Okay, so this is why it is called steady state oscillations. Okay, so we'll continue inshallah next time. Any questions from online? Yeah, see you. There will be a makeup exam for those who were absent in test 1. The suggested date is Sunday, next week. I know you have some exam this week, so it will be next week Sunday. And I don't know, after 3 maybe. Okay, I will think about the time. Massive.